So today we have Professor Pedro Assis, who did his degree here at IST and his PhD here, and most of his research in earlier years were in cosmic rays. Always with a growing interest on medical applications of particle physics technology, and that's what he will be talking about today in the context of a recently started project under the funding of the European Innovation Council. So thank you for
coming. Thank you for the welcome. Okay, so as Guilherme said, this is about particle physics and health, applications to health, and I will try to tell you how we pass from this to medical physics and to applications and to technology. In fact, I was always doing research in cosmic rays. I was always connected to the technological aspects of it, either through timing to the 10 nanosecond precision, or to understanding the detectors and so on, involving detectors, simulation, hardware, electronics, and analysis. So for this, I need to tell you a little bit about cancer. So it's just a very, very brief introduction. So typically, the cells are multiplying and dying, and sometimes there are mutations and the cells grow uncontrollably. If they stay together, that's a tumor, and if they spread around, it's a malignant tumor, meaning cancer. You can see that this is the definition of World Health Organization, and you can see in the steps that you will have some mutation somewhere in here. So, what are the characteristics of cancer? They can escape cell death and they can evade immune system. So, if a cell mutates, the immune system will take care of it and kill it. Or it can mutate and it's so strange that it cannot survive. The problem appears when a mutation is viable and it can evade the immune system. What will happen to cancer? Cancer will have a rapid multiplying rate. It will need lots of nutrients and it will develop vascular vases to grab nutrients. And so that's one of the characteristics of the cancer. And also it needs a strong oxygen intake. How do you treat them? It does depend a lot on the cancer and what you can make. So this systemic therapy, including chemotherapy and more recently hormonal treatments and biological therapies, these two are basically triggering the immune system to attack those cells, to make them recognize them as malignant, and chemotherapy is chemistry trying to kill these kind of cells. Then you have lots of strategies to go on. Many of them are based on sugar. You attach something to sugar. It's the way PET also works. You attach a beta plus emitter to a glucose molecule, and then it will go more to the cancer and less to the healthy. Then you can do surgery and you remove the mass. Of course, some of them can still be there, or you can do radiation therapy. Radiation therapy is giving radiation to the cells and killing them. It's not as simple as that. So you give radiation to the area and to the cell, and you make something, you make some damage within the cell. The cell doesn't die immediately, and what happens is that mostly the mitosis is prevented. So it won't replicate themselves, and at a certain point it will die. You induce the cell death, and then you have the shrinkage of the tumor. Problem. main problem this is radiation is not specific to cancerous cells and can also damage healthy cells. However, if you kill healthy cells, if you, for instance, in the skin, you remove some of the cells, it will regenerate and build up. And the tumor, in principle, won't do that. Tumors will divide more slowly after this radiation treatment. Challenge: to increase the therapeutic index, meaning kill more cancerous cells and spare more healthy ones. I will go through this talk showing you two of the main ways to do this. You can deliver radiation to the target volume and reduce the mean dose to healthy tissues, or you can take advantage of different characteristics between healthy and tumor tissues, although this is very hard. Disclaimer: these medical applications, most of the times, the process is not well known. We know it's observational, so we know this happens. We sometimes don't know how the mechanism is behind it. So, I took this from the master classes in proton therapy. There is a small program that you can download if you want, which is called MATRAD from DKFZ in Heidelberg, and I think also from GSI, where in MATLAB it allows you to program a treatment with radiation therapy using photons or using protons. So, sorry for the image. So, I promise you this is visible in the slides. So here you have a plane of a CT scan, and somewhere in here you have a tumor, which is represented in here in purple. This is a section like this, and so you have here is the spinal cord. You want to irradiate the purple, and you want to spare the liver, the kidney, and the spinal cord, so organs at risk. If you do this with photons, everybody knows that photons will interact with matter and deposit some of their energy, so you have a beam that is going to be attenuated, and depending on the matter, you can contain it or not, but a beam entering from in here will give this profile of those. So you see lots of those in here, and, well, a small amount of those in here. So typically, if you want to give radiation to kill the tumor here, then all this part will also suffer a lot. And so, why? I'm not conforming the dose to the volume, and so this volume is not optimized. What can we do? We can fractionate in space, meaning now I have, sorry, I forgot how many beams I generated. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And now you can have a high dose in here, you kill the tumor, and in here it's not that much. Of course, this is just playing with the program. This is not professional. It is completely forbidden to be used in clinical, but you can study this and understand what you are doing. Of course, I was careful enough not to put a beam in between here. Why? Because in that way I will deliver those to the spinal cord, which it's an organ which is more risky to give radiation to. In the intersection, of course, high dose. Now, you can do this regularly, so medicine is doing this for a long time, and so they fine-tune by trial error the dose and the dose rates, so they know which dose kills the tumor, which dose is more safe to healthy tissues, and how you do and there are protocols. And you give the dose at a certain dose rate, and then you repeat the treatment, and sometimes you can change a bit. However, there is an observation which is if you deliver the radiation at ultra high dose rates, the healthy tissues are spared. Nobody knows why. Okay? But there is an observation, several observations. Now comes the, let's say, the most impressive part. You do this on mice or pigs and so on and so forth. But there are illustrations where you can see really it happening. Timing of this stuff. So 10 to the minus 15 seconds, you are in the physical part. So you give radiation and so on and so forth. Then you have a chemical part where you can form radicals and so on and so forth, and you have alterations in the molecules. Then these will interact with the cells, and then you have a biological step at some point from hours to days to even years. And so you can make a radiation therapy treatment and then stay for 1 year or so, still recovering from the effects, and meaning the treatment is still making some effects. If you compress everything, then you are operating in here. If you have very high dose rates, you are in this region. And what is it, these flash beams? So conventional, you give this kind of dose, 0.1 gray per second. In flash, you give 40 grays per second. You deliver the same dose, around 10 to the 9 particles in minutes or so. And in flash, you deliver these particles 10 to the 9 in few seconds. Meaning the pulse must be very intense with very short pulses. Also means that your time scale is from minutes, where you can even think about making a correction yourself, to microseconds or so, where you cannot take a decision. And so what do you need? You need to monitor the beam and have automatic corrections if needed. For instance, if the machine goes wild and doesn't stop the operation, you need to know quickly to stop it. Okay? Otherwise, you are giving too much radiation to a person. So, what is standard? So, you have typically a nozzle, you have the patient somewhere in here, and you have an ionization chamber in here. Ionization chamber is basically a gaseous detector where you have 2 electrodes, you have a high voltage, pairs of electrons and ions are collected, and you are generated, and you collect them one from the top to the top and one to the bottom. You have a modest high voltage, so you don't have amplification in the gas, but you have lots of pairs created, and so you can estimate what is happening. Problems. If you create too many pairs at the same time, you mess with the with the electric field, and then you have saturation effects. And if you don't have an electric field to pull them up, they will stay close, the electron will stay close to the ion, and then they recombinate, and then you don't see it. And so you have a saturation effect. For the same dose, if you push up the rate, then you have saturation effect. So, ideas. That's something that LEAP group is working on for Atlas. So hopefully everybody knows the Atlas. Everybody knows LHC, right? Okay. Atlas is one of the experiments, and what is happening? It's transitioning. So this is the experiment. This is where the collisions happen, and it's transitioning to what's called the high Lumi phase of LHC, meaning it will have lots and lots of collisions in the same bunch crossing. So it's not one proton versus one proton, it's a bunch versus a bunch, and they will interact a lot along a line. And so you have all these particles. When you want to do tracking in this zone, one way to separate them is by timing, meaning 30 picoseconds or 100 picoseconds time resolution here. And this is the novel detector that is being developed. It's called high granularity timing detector. to discriminate the pileup. And so some state-of-the-art research, there's a detector to transport to medicine, LGADs. These are being used in these high lumi. They are silicon devices. They are very fast to the 100th of picosecond, and they will be very near the beam pipe, and so they will get a lot of radiation, and so they need to be radiation hard. And so this is a solution to monitor those kinds of beams. So we will get signal in the sub-nanosecond, which is more than enough to control this kind of beam. So that's one solution. Use LGADs, and first tests are ongoing with Rui Fernandes, who is doing his PhD thesis in collaboration with DKFZ in Germany. Second, I've been working in cosmic rays. When a cosmic ray enters the atmosphere, it's very energetic and it produces a shower. And it's a shower of particles that travels through the atmosphere, and it's exciting the atmosphere, producing fluorescence. But at the same time, they are traveling faster than light, and so they produce Cherenkov to the front. On the other hand, we use detectors that are tanks of water, and when particles pass through the water, they produce faint pulses of Cherenkov. And so the idea came to take this, can we do something with this? And we came with the FlashGuard concept, which is a beam monitoring system designed for ultra-high dose rate beams, enabling the safe implementation and clinical translation of Flash RT. So, sorry for the language, this is commercial, and so not trying to selling to you, but trying to sell to other people. The concept was developed 2 years ago or so. We filed for the patent. The first report is very good. We are doing a proof of concept, and who's involved is Gonçalo Ribeiro. He's doing his PhD thesis and master thesis in the PhD fast track. Carolina Miranda, now master student, but it was her work of PIC, and Gonçalo Rores, who is a PIC student. Gonçalo is doing the part of the instrumentation. So, now, what is Cherenkov? So, if you have ducks sitting, okay, so just going up and down, you see waves are traveling, right? But this guy is going to start walking in this direction. Watch what happens. So, see, you have a build-up. Sorry. you have a build-up of waves here because he's traveling faster than the waves are traveling. And so that's the principle of Cherenkov. So you have a threshold, which is basically this: when particles are faster than light. You have here the definitions if you want. After that, photons are emitted along a cone, and the number of photons will depend on the mass that is traversed. So if it goes this way, it produces a number of photons. If it goes like this, it's more or less proportional. I just put it here so you can look at a complicated formula, but it doesn't say much. Basically, Cherenkov will produce a spectra of different wavelengths that you might want to integrate according to your sensor. Okay, two applications. For protons, what do we want? We want a material that has a very high refraction index. Why? This means that light travels very slowly in there, and so it's easier to have particles that have a speed which is greater than the speed of light in that material. We found two of them. One of them we don't like so much, so let me focus on the nice one, which is diamond. And so diamond, it's a suitable candidate for this kind of stuff. Zircon is also usable, but it has disadvantages. For electrons, we don't want to disturb them. They are light particles, and so it's very easy for the energies in the treatment to find something which has a refractive index near the threshold. We want stuff that don't bother the particles, and one of them is aerogel. How do I know about aerogel? Nobody knows about aerogel. Anybody has one? So it's also used, okay, people in the team don't count. So, particle physics experiment. In the space, in International Space Station, AMS uses this to measure particles, uses aerogel. And so, that's our selection. What is aerogel? Is this very, very light, but it has a refractive index near the air, but works. And we estimated the Cherenkov. I'm not showing you all the simulations and so on and so forth. There are parts that you can calculate. There are parts that you need to do a simulation. From what we see, we have little impact on the beam, and I will get to this on a moment. You see that the field lines are previous to our device, and the dashed lines are previous to our device, and our device just introduces a little shift in it. What are we doing also? We are assaying silicon PMs, small devices, to record this light with precision. So Cherenkov is prompt in the picosecond region. These devices will have nanosecond resolution, and so we can monitor this beam with few nanoseconds resolution. This is the program. This is a commercial product, or intends to be a commercial product. So this is the team: me, Patricia and Bernardo, Gonçalo, Carolina. Sorry, I was going to say Catarina again. And Gonçalo Rores. And this was yesterday. So we were presenting at Técnico Innovation Center in the lab to market final. And we won it. So we were competing against trains and against stuff to put out in the water for wind energy and so on, and printable food, and we were able to win this prize. Changing a bit the subject, charged particles. So photons go and sometimes they interact. They can interact by three effects mainly, and transfer energy more or less randomly. However, charged particles, they go and they interact directly with the electrons on the medium. And so they do small kicks and they transfer a lot of energy. What is the dependence of this energy deposition or transfer with the speed? What do you think? Faster particles deposit more energy or less energy? Faster deposit less energy, right? But they go faster, and then they deposit, and then they get less and less energy until they are almost stopped, and then they deposit all the energy, okay? So that's something that we can use to our advantage. You see here the energy deposition. Look out. This is the kinetic energy, but it's in a log scale, and here it's in a log scale. So, what will happen? So we start with 100 MeV, and, we start with 100 MeV here, then we go forward, but now we have a little less energy, and we are here, we deposit a little bit more. Then we are here, we deposit a little bit more. Now we are almost stopped, so this is depth. We are almost stopped, and particles deposit a lot of energy. And this is called the Bragg peak. We can take this to our advantage and do something like this. This would be what we get with photons, and this would be what we get with charged particles. And if we are, I don't say lucky, if we know enough, we can fine-tune this and put it there. So, of course, we won't use only one energy. We use lots of these peaks, and then we construct these kind of profiles to irradiate the organs. And we can have stuff like this. So remember, this was our problem. This was our solution with photons. This is our solution with one proton beam. Okay? Only one. Of course, you can do others and others, and you see, I just put it through here to show you that you stop the beam in here, although there are problems in here. You stop the beam in here, and you don't go to the spinal cord. And so this is quite important in many applications. This is one of them. There is a cancer, kind of leukemia, that you need to irradiate the spinal cord, basically. And with protons, you can see here with photons, you have those everywhere, and with protons, you don't have. This is extremely important in pediatric cancers. Why? Long-term effects from radiation. So you are treating, but in here, you can induce a mutation, and then some years after, it can develop nasty problems, meaning cancer. And in here, you are sparing these kids to that. How is this in the world? Is it being used? These are the therapy centers a few years ago. Let me draw your attention to Heidelberg and to Marburg, where we are cooperating. And you will have in Spain around 10 to 11 centers, and in Portugal it's being planned one in Porto, in Instituto Português de Oncologia. So, about what was promised on the title, BoneOscopy. This is a project funded by Horizon Europe. It's an European Innovation Council grant, the Pathfinder. So it's the first stage to develop this to be a commercial device up to the end of 2029. Budget is 3.4 million euros. For Portugal, we have 500,000 euros. And this is what we want to do. We aim to revolutionize the treatment of bone cancer using proton therapy. So, we need to understand that even bone is a living organism, and so you have cells that will repair bone, meaning make it grow, and you have cells that are dedicated to destroying bone. And so from this balance is what is happening. So if you break a bone, so most of you probably broke a bone, you put it quiet and wait for it to recover. Building up bone, the organism can do that. Sometimes these osteoblasts go crazy, and then they do this. So this is an X-ray, and you can see there density, a low density on the bone. Why? Some cells went crazy and started eating away the bone. So, can we estimate the calcium concentration? Yes. So, if you look at this paper from Heidelberg, from the group of João, you have here a proton therapy machine, you have here targets, samples, and you have here crystals of cerium bromide coupled to photomultipliers. And what you do is that you have different samples with different compositions, and then you shoot protons there. So what's happening? You excite the calcium, and calcium will emit lines in here at 1.6 something MeV. And if you detect this signal, then you can have gammas versus calcium concentration, and you can estimate the concentration of calcium that you have. Why? You have this bone metastasis, and you have this proton therapy treatment. What is it going to do? The aim is to kill the cancer. And you don't regenerate the bone, but you stop it from being destroyed. These treatments are typically over some weeks. So, you prescribe an optimal treatment, which is this solid line. So this is the optimal treatment, and you will have sessions in between here. And so what is done? You make a CT scan before the treatment, and you make a CT scan after the treatment, and you have here the sessions of it. You cannot do a CT scan during the treatment for several reasons. First one, you cannot give the patient so much radiation from X-rays used to make the CT. The other question is logistic. To make the patient put him in the treatment room and then taking him out to the CT and so on and so forth, it's inconvenient for the hospital and it's inconvenient for the patient. So you cannot do that. What do we plan to do? We plan to provide measurements of these. Each time a treatment is made, we provide the number, the density of calcium. And so you can understand if you are in the curve of the optimal treatment, meaning the calcium goes down, but when you kill the cancer, the calcium stays the same. Or it might happen that you treat the cancer with 2 sessions. And then what happens is you stabilize your curve here. So what should be done? You should stop the treatment, not to give more radiation to the patient than needed. On the other hand, you have this bad stuff happening here, where if the treatment is not effective, it will continue as if no treatment was being given. And at a certain point, you have to decide, okay, I'm deviating from the optimal treatment, and so we need to reassess, either change the parameters of the treatment or don't inflict pain because it's not doing any good to the patient. How do we do this? We do it with prompt gamma spectroscopy during the proton therapy, and we want to provide daily monitoring to the plant, to the facility doing this. How do we do this? There's not so much that I will show you. Part of it I cannot show you because it's classified. And so, João, for instance, we have converged on a different solution. This is the one that I can show you. Why? There is another group doing the similar things, and so we cannot show you this. So the idea is that you get a patient and you get some detector. This is the proton therapy. Of course, we will do what? Samples of different concentrations of calcium to test the concept and to understand if it's feasible. This is a project that has high risk, high gain. And so it might happen that there's something, a showstopper that doesn't allow us to continue. So what's the detector? This part I can show you. So here you have crystals, and in here you have tungsten plates. What will this do? The tungsten plates will act like a collimator, focusing, meaning you only see from this point, and this point being what you are treating. So you know where the Bragg peak is, you point there, and in principle your signal, what enters the detector, comes from that region. Then you have crystals in here to maximize the interaction probability of these prompt gamma photons, so these 1.6 MeV photons in here, and it will provide light, and you collect this light. Of course, you need enough light in here, and you want good probability because you want to measure the energy. The much more light that you have, more resolution on the energy you have. Now, problems. There is a lot of background in here, and so you need to select. I think I have it here, okay. You need to select it by energy and by timing. What's missing here? Somewhere in here, there's this beam trigger fiber detector in the nozzle, so protons come from here, they will arrive to the patient, gammas come from here and arrive in here. These will provide the timing of entry, and these will also provide the timing, and then the AQ will only collect data in the time that we know that should be there. And so these will minimize noises. So the challenges are, we have small signals, so the signature is small. We want to select with energy, so we need a good energy measurement. We want to select it with time, resolutions of the order of 1 nanosecond, which in medical it's not common. We want to have the best primary detector. We want to have a nice trigger detector, but in fact we don't need to measure the energy, we only nor the position, so we only want to mark the entry. And so if it's a timing detector. We want fast electronics in all detectors, and we want to pack it to be easily translated to clinic. You cannot have a huge machine that takes a whole room because you already have the treatment machine there. So about the trigger detector, LIP has a long tradition in scintillators and scintillating fibers, and we want to use these to do something that we are currently evaluating. We are developing the concept. Which material? It must be fast in the response. It must generate light in a fast way so we can give the signal back to the main detector. Which granularity? For me, and typically you only need like a block, and so one channel of acquisition. But you can have pile up. There's a very strange thing that you talk to the guys from the machines and ask, what's the timing distribution of the beam? We don't know. That's the answer. And so they know the frequency that they give you. They know that particles are from here to here, but the extraction, they cannot guarantee that it's exact. And so you have particles that are distributed. So you can have particles on top of particles separated by less than 1 nanosecond. And then perhaps we have to do segmentation, because if you have two detectors segmented in space, then if one particle hits this one and the other here, then you have two signals and then you can play around. If you have only one, you add them up and you can get like a signal that comes up, stays up, and then goes down. Okay? Light detector. We want to use silicon PMs, but we need to understand if we can cope with the noise. They have a lot of intrinsic noise from temperature. Or we can use PMT, but if we have one channel, that's not a problem. If we have many channels, PMTs are probably not an option. Electronics is also dependent on how many channels. We have ideas, but we need to develop the electronics on the nanosecond scale, which is 1 order of magnitude of what we are used to in the electronics lab at LIP. So that's it. This is the consortium. Let me just leave the expertise of LIP. So LIP is in the project because we know how to simulate physics and understand what's happening. We know about detectors and we have fast instrumentation. And so we count with the support of LOMAC, which is the Laboratory of Optics and Scintillating Material from LIP. We count with the support from the electronics laboratory of LEAP. Also, we will work with the mechanical workshop of LEAP because they are very precise and they can do very precise, not production-like, but they can find the solutions that we need. And also, of course, with the competence centers in simulation and big data for the simulation and analysis of these kind of events. And so that's it. Thank you for your attention.